In our discussion in the last couple of lectures, we have been looking at how the feedback mechanism in digital circuits can be used as one step above combinational circuits to to realize multiple functions. One of them is to make circuits act like memory elements. That is, um, the circuits can store the output or the state so long as there is some kind of a user signal. So therefore we have seen different circuits, the basic block of which is called as the latch, the basic butterfly structure using two NAND gates. Thereafter, what we did was we modified this latch into having something called as an enable signal, where this latch operation can be divided into two halves depending on the enable signal value. One is it acts like a latch depending on the user inputs when the latch is enabled, and when the latch is not enabled, then come what may, whatever is the user input to the latch, the output will still remain the same as the previous state. So that was called as the gated latch. Say for example, we looked at the SR latch, we looked at the D latch. So effectively what we saw was that there is an additional input called as enable input. This enable input is additional to the user inputs. So effectively what is happening, we saw was that enable equal to 1 indicates latch enabled, and enable equal to 0 is that the next state is always equal to the present state, that is latch disabled. So effectively you can also have active low enables. In general, that can be possible. Now, latch is a circuit, whether it's a latch or a gated latch. In particular, the gated latch is a circuit which is sensitive to the enable signal, which is sensitive to the enable input. Depending on whether the enable is 1 or 0, the latch will be enabled or disabled. So therefore, these circuits are also called as level sensitive. Level sensitive to the EN signal. So then, is there something through which we can have any other kind of sensitivity to EN? The next step after gated latch is to introduce a timing constraint. Introduce a timing factor where the behavior of the latch does not depend on the values of enable, but rather the transitions of enable. Now, why am I talking about transitions? If If let us say enable is 0, it looks like this. If enable is 1, it looks like this. So this is the time, let us say, when enable is 0. This is the time when enable becomes 1. Okay, so effectively what we are seeing is that while it is very interesting to have this kind of a feature to control the operation of the latch, these values of enable don't really convey us any time information, or rather they don't provide us any time control on the circuit. Why? Because this enable is equal to 0 is there for quite some period of time, that is this much period of time. Similarly, enable is equal to 1 is there for this much period of time. Now let us say we want to have a circuit where the changes in the circuit will happen at specific instants of time. Now it's very difficult to find an instant of time, of course, there are infinite instances of time in this region. It is very difficult to find that. Maybe one distinct time instant where we can do some operation. It's not impossible, but it then becomes very big, finding a time instant in either this region or this region. So therefore, we can use one more feature of this enable signal to convey specific instants of time. That is, we will look at the edge of the enable signal. Now edge can be a low to high edge, or it can also be a high to low edge. So let us say if my enable input looks like this, this and this instance are where I have low to high edges. You can see this is an edge. Since these transitions, they're happening almost instantaneously, the slope of these lines are nearly infinite. So therefore these transitions essentially convey information about specific instances at time, because here delta t is almost equal to 0, the time taken for the transitions. Likewise, these ones are high to low transitions. These are high to low transitions. Now we will say that we are going to modify the circuit of our latch in such a way that it becomes sensitive to the edges of the enable signal, not during the levels of the enable signal. That circuit, okay, that circuit is called as a flip-flop. A latch whose operation is sensitive to the edge of the enable signal, okay, that is called as a flip-flop. So a low to high edge, that is when initially the enable is low and then suddenly it becomes high. This low to high edge is called as a positive edge, because the slope of this line is positive infinity. And high to low edge indicates this, when initially the enable is high and then it becomes low. This is called as a negative edge. So therefore, a flip-flop is a latch that is sensitive to the edge of the enable signal. So sensitive to either positive edge or negative edge of EN signal. This kind of circuit is called as a flip-flop. Now in the previous lecture we looked quite in detail about what some of the latches look like. Let us say, for instance, I'll use the D latch we already discussed that the D latch is quite popular over the SR latch because it has the memory capacity, it has the memory property, and at the same time it is able to avoid the forbidden state of the SR latch. So therefore, if you recall, a D latch looks something like this. This is the enable input. The D input is over here, and the complement of the D input essentially goes to the lower NAND gate. So this is what the internal diagram of a gated D latch looks like. So now onwards, we will show the latch just as a black box, kind of like an MSI circuit, and that latch essentially is represented in this form. The two inputs are there, D and enable, and there are two of the state variables, Q and Q bar. This is how latches are represented in form of a diagram. Now, if I have to represent a flip-flop, the thing is, we need to show that the enable signal is sensitive to the edge of the signal, or the flip-flop is sensitive to the edge of the enable signal. Now, in all our discussions in the last 20 odd lectures in the course, never have we come across a circuit where that circuit is dependent not on the actual value of the signal input, but rather on the edge. Now, this is a concept that is very, very new for us. This is a concept that is very, very new for us. So therefore, we have to see a way in which this property can be represented in form of a black box. So let us say I have a positive edge sensitive. Edge sensitive is also called as edge triggered. So if I have a positive edge triggered D flip-flop, it looks like this. However, over here, the enable is shown slightly differently. It is shown somewhere in the middle, and there's an arrow like this. This indicates that it is sensitive to the positive edge. Whereas if you have a negative edge triggered, it looks like this. There's a bubble and then this arrow. This is the enable. In case of a positive edge triggered flip-flop, you have simply an arrow like this into the body of the flip-flop. In case of the negative edge triggered flip-flop, you have an arrow and before that a bubble which indicates a negative edge. Now, the next question is, what is the difference in the circuit between a gated D latch and a D flip-flop? That is, how can we convert this latch into a flip-flop? Well, that is not so easy. That is not so easy. There are multiple ways to do this. However, we shall not be discussing them as part of this course because those concepts are a little bit, some of those concepts are a little bit high end and they are dependent on a lot of other factors. However, if you study them very closely, you will see that it is not very difficult. So therefore, I encourage you to go back and look at either books or online sources which show you how you can realize a circuit that is sensitive to the edge of the signal rather than the level of the signal. Or in other words, is it possible to convert this gated D-latch into either a positive edge-triggered flip-flop or a negative edge-triggered flip-flop? As far as the course is concerned, we will simply assume that these are there for us. We will see how these two work actually, and then we will see how to make use of these flip-flops as black boxes without going into too much detail about how we are achieving the edge triggering function. So let us take an example. Let us take an example and see how a D flip-flop works when it is positive edge triggered and when it is negative edge triggered. This is what the D signal looks like as a function of time. And this is what the enable signal looks like. This is what the enable signal looks like. Now let's quickly write down what the state table of the D flip-flop or the D latch is. So state table wise, nothing changes. A flip-flop is still a latch, so the state table is the same. However, the way it operates is different. Now suppose this was a latch. This was a latch with an active high enable. So therefore, I would look at those places where enable is high. That is here, here, and here. So therefore, if this was a D latch and if you initially assume that Q was 0, until this point, it will continue to be 0, the old value. Now over here, what is happening? In the time when enable is 1, D is changing like this, high, low, high. So whatever is the value of D, that will be the next state. So therefore, it will look like this. Now, at this point, the enable is becoming 0. So as long as enable stays 0 for this time, the state of the latch will remain same as the old state, that is 1. So it will continue to remain 1 until this point. Again over here, the enable is becoming 1. So here whatever is the value of D, that will be the value of Q. So this will go to 0. It will stay till 0 until the next time D changes, that is over here. So it will obey this change, and again it will come back like this and stay 0 until the next time enable is becoming 1. Okay, so over here the value of D is 1. So now this will increase to 1, and then again over here it will come back to 0 and it will stay this way. Now let us assume now that this D and EN are inputs to a positive edge triggered D flip-flop. Now if these two are inputs to a positive edge triggered D flip-flop, what will happen? So I will now mark the positive edges using arrows here, here and here. There are 3 positive edges in the enable signal which I can see from this diagram. So again, if you assume initially that the flip-flop state is 0, now look at only what is happening at this edge. At this edge, the value of D is 1. So therefore, if D is 1, the next state will be 1. So far, it is exactly the same. But this will stay like this until we get the next edge. Here, we have changes at specific instants of time, that is dictated by the enable input. So this Q will continue to stay as 1 until the next positive edge of the enable input. Now over here in this next positive edge, what is happening is that we see D is 0. So therefore, if D is 0, the next state will also be 0. And this will continue to stay until we get the next edge. The next positive edge, that is like this. And it will continue to stay 1 until the next edge comes. The next positive edge comes in the future. So we will leave it like this. Now, let us consider the converse. Supposing this D and enable were inputs to a negative edge triggered flip-flop. So therefore, now we have to see which are the negative edges of the enable signal. Here there are 2. Once again, if we assume that the Q is 0 initially, we will wait until we get the first negative edge in the enable input. So what we are seeing during this negative edge, D is equal to 1. So therefore, if D is 1, the Q will also change to 1 and it will stay like this until the next negative edge, that is over here. So over here in the next negative edge, we see that D is 0. So therefore, this 1 will continue to remain as 1 over here and it will come to 0 like this at this point. And it will stay 0 until whenever the negative edge is coming. So we don't see it in this diagram. So we'll leave it the way it is. Alright. Please note that a flip-flop can be either positive edge triggered or negative edge triggered, but never both. You can have flip-flops which are positive edge triggered or negative edge triggered, but not both. Just like you can have a latch which is active high enabled or active low enabled, but not both. Otherwise, there is no real sense of having that kind of a circuit. Now, when we look at flip-flops, The only difference between the latch and the flip-flop in terms of operation is that the latch is level sensitive and the flip-flop is edge sensitive. And edge sensitive for which signal? The enable signal. So therefore, when we look at a flip-flop, we see that it is actually responding to the edge of the enable input. So therefore, it is not really proper to call it enable anymore, because the flip-flop does not really depend on what is the final value of the enable, but rather the transitions. So therefore, this enable word is used only for latches. For flip-flops, the enable signal has a rather different name. The enable signal is called a clock signal. It is called as a clock signal. Why it is called clock? Because it conveys the timing information. It denotes or it communicates to the circuit, to the flip-flop, that okay, this is my signal and my edges are over here, either positive edges or negative edges. And you have to respond to these edges only, that is in these specific time instants only. Therefore, this signal is called as a clock signal. So, let us say I have a positive edge triggered D flip-flop. It will look like this. This arrow will show that it's a positive edge triggered D flip-flop. Okay, so this is what it looks like. This is what it looks like. Now, in our discussion so far, we have seen two different kinds of latches. One is called the SR latch, the other is the D latch. We saw that the D latch can also be used as a flip-flop. Even actually the SR latch can also be used as a flip-flop. Although we did not see that example very closely. We took a D flip-flop as an example. But in general, a latch can be converted into a flip-flop. So you can also have SR latches. You will have SR flip-flops. You will have D latches. You will also have D flip-flops. So the question is that in addition to all these latches and flip-flops that we know, are there any more flip-flops that we should know about? Yes. Yes. There are two more flip-flops, okay, which are very commonly used. They are not latches, they are only flip-flops. So the next flip-flop that we are going to see is what is called as a JK flip-flop. It's called JK after the person who designed this flip-flop, and his name was Jack Kilby. So the state table of the flip-flop, let us write. So whatever is the latch or the flip-flop we've been studying so far, we have been writing its state table first. So let us say J and K are the inputs to this flip-flop, kind of like how we had for an SR. And then we will write the next state. Once again, I am not going to go into what is the detailed circuit of this flip-flop because it's a little too complex. So 0, 0, 0, 1, 1, 0 and 1, 1. For different values of J and K, you will get some future state value. So when J and K is 0 and 0, this is Q. So it looks kind of like the SR latch or the SR flip-flop so far. and when it is 0 and 1, when it's 0 and 1, just like the SR latch or the SR flip-flop, Q plus is 0. 1, 0, it is 1. So for these three cases, it is just like the SR flip-flop. The only thing is, when both inputs become 1 and 1, in case of an SR, the output becomes forbidden. So the JK flip-flop, just like the D latch or the D flip-flop, was designed to overcome that forbidden state. So here what happens is that the next state is a complement of the present state. The next state is a complement of the present state. Alright. So that is what the JK flip-flop looks like. That is what the JK flip-flop looks like. There is also another kind of flip-flop that is called as a T flip-flop, which is a subset of the JK flip-flop. It has, just like D flip-flop, it has only one input, that is T. So when T is 0, Q plus is equal to Q, and when T is equal to 1, Q is equal to Q bar. So in some sense, if you look at the first and the last rows of the JK flip-flop, you will get the T flip-flop. So these are two flip-flops which are used. The T stands for toggle. So the meaning of toggle is that when you have T equal to 1, the next state is the complement of the present state, just like over here. So therefore, the next state can be made a complement of the present state. So it's like saying the states will switch, and that phenomenon is called as a toggling phenomenon. Okay. Now let us look at these two flip-flops in some more detail. Let us see how we can derive the extended state table, and from that the excitation table of each of these flip-flops. Let us look at the T flip-flop. Let us look at the T flip-flop. This is what it looks like. So from this, we will try to draw the extended state table where the next state will be a function of T as well as the present state. So when T is 0, what will happen? Q plus will be equal to whatever is the value of Q. So it is 0 and 1. When T is equal to 1, Q plus will be whatever is the complement of Q. So here Q is 0, 1. Here Q plus will be 1, 0. Now, for the excitation table, we have to write Q and Q plus, and from that we will try to extract the value of T. So when Q is 0 and 0, what is the value of T? It is 0. When Q is 0, 1, sorry, Q and Q plus are 0, 1, that is over here, the value of T is 1. When Q and Q plus are 1 and 0, that is over here, the value of T is again 1. And when Q and Q plus are 1 and 1, the value of T is 0. So this is the excitation table for the T flip-flop. Let us derive for the JK flip-flop. Let us see how to derive the excitation table for a JK flip-flop. So the state table looks like this for a JK. So then we will write the extended state table where the inputs will be J, K and Q, and we will try to see what the Q plus is. Once again, I will emphasize that Q and Q plus are not different. They are the same signal but at different points in time. Okay, so when JK are 0 and 0, Q plus will be whatever is Q. Let me divide them this way, then it will be easier for you to appreciate. So here in these two rows, JK is 0, 1. So the value of the Q plus will be always 0. For these two rows, JK is 1, 0. So the value of Q plus will be 1 for both cases. J and K are 1 and 1. So Q plus will be complement of Q, that is 1 and 0. Just the opposite. So from this, let us try to get the excitation table of the JK flip-flop. So on the left side, we have Q and Q plus, and on the right hand side, I will write J and K. We will try to see for the present state that we know and the next state that we want, what would be the values of J and K required to make that happen. So we will say 0, 0, 0, 1, 1, 0 and 1, 1. So when Q and Q plus are 0 and 0, which are the cases? Q and Q plus are 0, 0 here and here. Alright. So this will be just the same as that of the SR flip-flop when we had derived. We saw that for these two rows, J is 0 and K does not matter. It is 0 and 1. So therefore, the required condition will be 0 and don't care for J and K respectively. When Q and Q plus are 0 and 1, Q and Q plus are 0 and 1. So cover these left hand columns just for the sake of clarity. So 0 and 1, 1 is over here, 1 is over here. So corresponding to these two rows, I see that one row is 1, 0, the other is 1, 1. So here J has to be 1 because both cases J is 1. And in one case K is 0, one case K is 1. So over here K does not matter. It is don't care. Because the value of K does not seem to affect the next state. Then when Q and Q plus is 1 and 0, again cover. So 1 and 0 is over here and over here. These two rows. So here we see K is 1 in both cases, but J in one case is 0, one case it is 1. So the value of J does not matter over here. The value of J does not matter, but K is 1. And the remaining two rows, that is when Q and Q plus are 1 and 1, these two rows, which are unmarked. Over here we see 0, 0 and 1, 0. So again J does not matter and K is 0. This is what is the excitation table for JK flip-flop. Alright. This is what it looks like. This is what it looks like. So what have we learned so far? In particular, we have seen 4 kinds of configurations or 4 kinds of flip-flop. First we saw the SR. which is called as a set reset. This can be a latch. This can also be a flip-flop. Then we saw the D, which is a latch as well as a flip-flop. It can be either. Then we saw JK. This JK is a flip-flop only. And finally, we saw T, which is only a flip-flop. Each flip-flop has two truth tables associated with it. The first is called as a state table, which is also called as the characteristic table, where the state variable is expressed as a function of the inputs. The second is called as the excitation table. The excitation table is a hypothetical table just for our own analysis, where we know, supposing we know what the present state is, and for a desired value of next state, what would be the values of the inputs that is needed to make that happen. Now, the difference between a latch and flip-flop is only that they are the same, except that the latch is sensitive to the actual value of the enabled signal, or it is sensitive to the level of the enabled signal, whereas flip-flop is sensitive to the edge of the negative signal, either the positive edge or the negative edge, but not both. So, I would encourage you to get familiar with the state table and the excitation table of each flip-flop, because we are going to be extensively using these for various kinds of applications over the next few lectures, and it will be very handy, or it will be very helpful if you have these state tables and excitation tables at your fingertips. We shall continue from this point onwards in the next lecture. Thank you.